Yo, I've got a question. What if it is matter? Like, what stuff is made of? Take this pencil, for example. Sure, it's made of plastic, but let's dig it a little deeper, shall we? Plastics are a class of material made of polymers, very large molecules composed of smaller, repeating subunits, like chains of molecules. Every object and every substance we interact with is composed of molecules. Every molecule is an arrangement of atoms. Different varieties of atoms can be mixed and matched together to create all sorts of molecules whose properties are defined and constrained by the properties and arrangement of its atoms. We used to think atoms were the smallest unit of matter, which is where they take their name from. In ancient Greece, it was widely accepted that all matter was composed of four elements: water, earth, fire, and air. These four elements were a continuum that filled the entire universe. There was no such thing as empty space. For this reason, the philosophy of atomism was widely rejected. Atomists thought the universe was filled with two things: atoms and void. Atoms came in an infinite variety of shapes and properties, and, separated by empty void, they were the microscopic elements that built up all of matter. When modern science discovered the existence of tiny, indivisible particles that all matter was made of, we thought we'd discovered these hypothetical atoms. It's only later we realized what we'd decided to call atoms were actually made of smaller particles, but could only be split apart using monstrous amounts of energy. We've since learned that atoms have a nucleus, composed of positively charged protons and chargeless neutrons, around which negatively charged electrons orbit. Since neutrons don't have a charge, they don't come into play in chemical interactions. Because the electric force between electrons and protons is how atoms bind together to form molecules, and how molecules bind together to form macroscopic objects. Like how gravity binds moons to planets, the electric force binds the electrons to the nucleus. In reality, it's a little more complicated than that because we're working at the quantum scale, but more on that later. Neutrons have no electric charge. Their role is to hold the nucleus itself together. If there was only the electric force, the protons would repel each other and wouldn't form a nucleus. There is a different mechanism between protons and neutrons called the strong nuclear force. The strong force is immensely, stronger than the electric force, which is why nuclei don't just break apart from protons repelling each other, but it only works on a very, very small range, just about on the scale of an atomic nucleus. It also goes one level deeper. Protons and neutrons are made of quarks. Two up quarks with one down quark make a proton, and two down quarks with one up quark make a neutron. One up quark has 2/3 of a proton's charge, while a down quark only has -1/3. These triplets are held together with a strong force as well. In fact, the interaction between protons and neutrons is really more of a side effect of the forces that hold their quarks together. Quarks are a part of a larger family called elementary particles. They are called elementary because, as far as we know, they're the smallest components of matter. The particles of matter are called fermions, composed of the 6 quarks, as well as another family called leptons, which electrons belong to. There's also another group called bosons. The bosons carry information, forces, and energy between the fermions. For example, the electromagnetic force is carried by photons, the strong force by the gluons, and the weak force by the W+, W-, and Z0 bosons. Some theories say that gravity is carried by the graviton, but that particle has yet to be observed and carries a heavy string theory baggage that I'm not qualified to talk about. We have a pretty exhaustive list of every particle that makes up stuff, which we call the standard model of particle physics. This is what stuff is made of. But that's not quite what I'm asking about. It's like I have a model kit with a catalog of all of its pieces. Sure, that's useful, but what I want to know right now is what plastic those pieces are made of. What is the plastic of quarks? Well, having no substructure has some weird consequences on their appearance. They're said to be point-like, which is to say they have no size, no volume. Physics describes them kind of like points with special properties evolving in space. But then, why does matter have volume? How does it occupy space if, fundamentally, none of its base components do? Just because elementary particles don't have a volume doesn't mean they don't occupy space at all. Fermions are distinguished from bosons by the fact that they follow Pauli's exclusion principle. Every particle is defined by the states in which they find themselves. For example, their position, their energy, and their spin. A particle can be found here or there, its energy can be high or low, and its spin can be up or down. Pauli's exclusion principle dictates that no two particles of the same kind can occupy the exact same set of states. If one position is occupied by an electron, you can't jam another electron with the same spin and energy in the same place. Bosons, on the other hand, don't follow this rule, but they don't compose matter either. Rather, they're the carriers of fundamental forces. By the way, these fundamental forces that act between fermions are another thing that define what we perceive as a volume. When you're pushing or holding an object, the reason your hand doesn't just phase through it is because the electric force between your electrons and the objects is pushing back. When you've got objects that don't have any size and touching something really only means that you can't grip stronger than electrons repel each other, our perception of reality kind of sort of begins to break down a little. Though, at this scale, thinking classically wouldn't do us much good. You see, elementary particles are quantum objects. They move following their wave function. Quantum objects are described by a wave function, a physical equation that tells us the probability of finding them in a given state or another. They only collapse into a specific state when they interact with an outside agent. What state they collapse into is entirely probabilistic. This makes the bond between electrons and the atomic nucleus a bit more complicated than that of a planetary system. Because electrons move following a wave function, they behave more like waves. How that wave function evolves in time under certain constraints, like, for example, the presence of an electric field, is defined by Schrodinger's equation. We can calculate what shape an electron's wave function will take around an atomic nucleus for specific energy levels, and thus we know where it can, probabilistically speaking, be found. The results are otherworldly. So if elementary particles are just mathematical points with specific mathematical properties that move according to a mathematical function, is that it? Is that the answer? Is the plastic that all matter is made of just math? After all, in physics, all of nature is described with mathematical equations. Pauli's exclusion principle, the properties of fermions and bosons, the forces through which matter interacts with itself, all have a basis in math. But I'm not comfortable taking that lesson. You see, science doesn't explain the universe. It just describes it. So to me, saying that the universe is math because physics is so, is kind of like a sketch artist saying that trees are made of graphite because he draws them with graphite. If physics is a code written in the programming language of math, then what does the computer it's running on look like? Studying the universe is like trying to figure out how a clock works without being allowed to look at the mechanism. We can only watch how it behaves and sketch our best guess of how its insides would have to be designed for it to behave like it does. The mathematics of physics is only just a drawing of how the universe's clockwork probably looks and how it seems to move. Will we ever be able to look inside the clock and compare notes? It's hard to say. Philosopher Frank Jackson proposed a thought experiment called Mary's Room. It goes like this. Mary is a brilliant scientist who is, for whatever reason, forced to investigate the world from a black and white room via a black and white television monitor. She specializes in the neurophysiology of vision and acquires, let us suppose, all the physical information there is to obtain about what goes on when we see ripe tomatoes, or the sky, and use terms like red, blue, and so on. She discovers, for example, just which wavelength combinations from the sky stimulate the retina, and exactly how this produces via the central nervous system the contraction of the vocal cords and expulsion of air from the lungs that results in the uttering of the sentence, "The sky is blue." What will happen when Mary is released from her black and white room, or is given a color television monitor? Will she learn anything or not? Could you, with perfect knowledge of color, explain the color red to a blind person? And could they, after the fact, in their mind's eye, see the color red? Could you, with perfect knowledge of how the universe works, understand its fundamental nature? Could we even obtain such perfect knowledge? Theoretically, to get it, we'd need measurement tools of infinite precision. But let's suppose we obtain it anyway. Except, unbeknownst to us, there's one gear sitting in a corner of the mechanism that doesn't touch anything. It's spinning, alright, like every other gear, but it's not connected to the rest of the clockwork. We'll never learn of its existence because it's got no effect on the clock face, on how the hands move and react. Yet, it's still a part of the full picture. If we don't know about it, we don't have perfect knowledge. So, when I ask myself what matter really is, what the fundamental nature of this pencil is, I'm asking a question that maybe doesn't have an answer. And if there is one, I don't know if we'll ever be able to find it. Maybe we'll spend eternity getting asymptotically close to a theory of everything. Maybe I'd like to take a metaphorical hammer and smash it into the metaphorical clock. Sometimes physics is frustrating, but physics is also fun. Cheers. Ah!